Welcome to statistics. We're going to look at binomial distributions. Now, binomial distributions, or distributions in general, are a way for us to be able to take our data and separate it in such a way that we can decide and make decisions and discover more things about what our data set is telling us. So we go out and collect the data set, and then we have the ability to do something with it. Now, binomials are special in that what they allow us to do is look at a fixed number of observations that have a fixed outcome for fail or success. Now, we put fail and success in quotes here because it's not necessarily talking about getting success or failure in the traditional sense, but in the sense of a value of P and a value of Q. So like flipping a coin to be 50-50, but in other situations, like a couple examples we're going to look at, it doesn't necessarily have to be that way. We could be looking at the success and failure of a particular engine, or we could be talking about birth rates as well, where we define success as the birth of a girl or the birth of a boy, in which case the failure would be the opposite. So you can obviously see that that's not necessarily talking about failure in the traditional sense that we are having an event which is bad. We're just saying that a wanted outcome versus the other outcome. And that's the thing to pay attention to with this, okay? So we're talking about a mathematical terminology. We're not talking about social constructs with these wordings and the terminology we're using. The probability, and this is one of the important pieces. There are two big important pieces of binomial. The first one is the number of observations is fixed. The other piece is that the probability of success is the same for all observations. So we can't have that probability changing. So for instance, pulling a card out of the deck and then pulling another card out of the deck, that would not be a binomial because the observational probability would change. Even if we're saying we're only pulling two cards out, so the number of observations would be 2. But if we're not using replacement, then the probability for success would change. Now, if we are using replacement, then of course we might be able to make it fit into a binomial situation, in which we're going to look at as well. So with binomial distributions, we have two parameters: n for the number of observations and p for the probability of success. Now, to run through an example of this, and this is a situation kind of what I was referring to in terms of failures and success not being a social value or necessarily even a win-loss situation as much as a wanted and the other outcome. And you have just the two outcomes. That's the big important piece of that. So maybe we just need to create better words than success and failure. But genetics says the probability of a child receiving type O blood from their parents in a particular family structure is 0.25. Now, that's not across the board. That's not a normal thing. They're just saying in that particular family, because the blood type of the child is dependent upon the blood type of the parent. So if both parents are type A, that changes the probability of getting type B blood out of the child. In fact, I think it makes it almost impossible. I'm not sure about that, though. So if we have 5 children in a family, that'd be n equal to 5, and then of course the probability of each child being type O would be 0.25. Therefore, this would be a binomial distribution because we have a fixed number of observations, which would be 5 children in the family, and a fixed probability, which would not change because of genetics. However the genes work out. So one parent has I think the way it works is you have 2 genes that determine your blood type. So one parent has A and B, the 2 genes that say type A, and when the other parent has 1 gene that says type A and the other is type O, and there's only one instance where that situation works out. The child only gets type O. I'm not sure on that. I'm not big on genetics. Sorry. Anyway, so that works out to how only a quarter of the time you expect or the probability is 0.25 for each child. Now, that's not to say that not all 5 children have type O blood. That is completely within the realm of possibility. It just means that it doesn't necessarily happen that way. It just means that's the probability that it could occur that way. So keep in mind that this is the difference between the probability of the event occurring versus the actual outcome. Okay, so let's keep those two pieces separated. So example number 2, the birth of girls and boys at a particular hospital. We want to talk about the fact that from one perspective, this could be pushed into a binomial distribution. In other cases, it wouldn't be a binomial distribution. So we're going to talk about that. The probability of having a boy just about anywhere in the world is 0.52, which is just over half the time, which is quite interesting. A lot of people think, well, genetically speaking, you have a 50-50 shot of a girl or boy. Yes, genetically you absolutely do. But it doesn't actually work that way in practice. When you actually look at the data sets, it's actually right around 0.52 in the United States and Canada. In other places like China, it's actually significantly higher for having a boy, the probability. And that is, there's some factors involved in that. But at one point in China, it was closer to 70, or 0.7 was the probability of having a boy in China. But that was based upon a couple of the bullet points down there at the bottom, which was revolving around parent choice now, or family choice. The idea being there is that's another way of saying controlled population, or however you want to put that. Certain countries have certain mechanisms in place that prevent the growth of families so that the population doesn't grow out of control. But the other side of this, if we're looking historically at this data set, n equals 100, and then you are looking at this being a binomial distribution. Otherwise, if we are not looking historically at a particular data set, we're just looking at the hospital in general, that's not going to be a binomial, even though we have a set probability, because the observations are not fixed. Now, we're going to look at what we can do with this here in a second, but for the most part, it's the best we can do is just say it's not a binomial because the observations aren't fixed. But the way we work around that is by fixing the observations to a particular value and saying, now that we have this as a fixed value, now we can start working forward. And you'll see why the fixed value is important here momentarily. Now, another part to think about this is another reason why it's not necessarily binomial is because, once again, P will fluctuate. If you're looking at a particular family that has two children, they're both boys, then it's not binomial because the family has the option of having a third child, and the family, there may be some other genetic factors involved in that. But also, as a result of there being two boys, you're already talking about the probability within that family not being 0.52 anymore. So the probability is not fixed for those observations. So again, this would not be binomial. So we'd look at a general set of this as opposed to individual families in those terms. So next piece of this, another way to look at this, we'll talk about the probability of a tomato, and we're actually going to work through some numbers on this one to give you some more examples here to work with. Tomatoes being damaged on shipment. Let's just say there's a shipment of 10,000 tomatoes and 10 are inspected. And the idea being is that we can't have more than a certain number of tomatoes that are damaged in such a way that they're not marketable before we refuse the entire shipment of tomatoes. So out of those 10,000 tomatoes, we're going to select 10, I keep saying tomatoes, potatoes, whatever, tomatoes. We are going to inspect 10 at random. Now you go back and how you randomly select 10, maybe you 5 different or 10 different crates, and you pick a random tomato out of each crate. They'll probably be on the top of the crate because that's the easiest thing. So it's not necessarily a random picking, but that would be the way we'd go about that. The probability, the historical probability more than likely, of the tomato being unmarketable would be 0.11, meaning that if we were to pick one up, that is the probability that tomato cannot be put in the store and sold because it is damaged beyond that spot. Doesn't mean it's not edible. It could just be bruised, in which case it could be very easily turned into paste or some other type of processed tomato product, right? But we couldn't just put that particular tomato in the store and sell it. So there's that, right? But it's when we look at what's going on with that, once we picked one tomato out of there, we don't have 10,000 tomatoes anymore. We have 9,999. Which once again changes the observation, and we're no longer dealing with a binomial distribution. So there are ways that we work around this. So you may think, well, what's the point of having binomial distributions if everything we are looking at here, once we change this process here, is not binomial anymore? Well, because we can work with it. And here's what we're going to do. First thing is we need a couple of pieces, namely the binomial coefficient, which then allows us to be able to get that third bullet point you see down there that allows us to be able to determine the actual outcomes that we're concerned with here. And we're going to do some stuff with here. Now, the first thing is we're going to, a number of ways that we're arranging k successes among n observations is given by the binomial. So essentially what we're doing there is we're creating the number of ways of arranging. Now, when we say arranging, then we're talking about a combination here, okay? And that's what that formula is right there, the n factorial over k factorial times n minus k factorial. There's exclamation points there, or a mathematical symbol called factorial, which means multiply that number by everything below it. K is how many ways we can do that. So how many ways can we pull 10 tomatoes out of 10,000? So by doing that, we have the ability to negate the fact that we're changing the number of observations. We can now set the observations up such in a way that it's not going to affect us anymore. That is just simply doing that piece, and that allows us to move forward with the rest of the information. The next piece is x. You see that last line there. We have p of x equals k. Now k is the number of ways that we're picking them. That's how many pieces at a time we're picking. So we're picking 10 tomatoes. We can also replace that equal sign with less than or greater than as well, depending on our purposes and what information we're wanting to know more about. So what do we do then next? Well, then we're talking about taking that coefficient, which is the number of ways, the number of different ways we can rearrange 10 tomatoes out of the 10,000, right? And then p to the k power, meaning probability of picking an unmarkable. Notice that, keep in mind here that the one we can't sell is the unremarkable, is the p-value right here. So this would be the success. We're picking one that we can't sell, which seems kind of backwards, but you got to remember what we're dealing with here is a process of what we want to determine versus what we don't want to determine. We want to determine how much of the crop is not marketable, how much of it is too damaged, right? So it'd be the success probability, which in this case is the 0.11 or 0.11 to the k power, in this case 10, right? And then 1 minus p to give us the probability of failure, and then that raised to another power, which in this case would be n minus k, or 10,000 minus 10. Now, to actually run through this in a couple ways, let's just think. Let's say we pull that those 10 tomatoes out, and we want to know what is the probability that one or none of them have any bruising, any damage to them whatsoever. What's the probability that we pull one or none of those 10 tomatoes have no bruising on them and that we can sell them, which means that 10 out of 10 are sellable, right? Or 9 out of 10 are sellable. Those are the two options. 9 out of 10 or 10 out of 10 are completely sellable, and we can make a profit off of those tomatoes. So what do we do? So the first thing we do is, think back to that formula we have there. This is all equal signs, right? So we got to switch. Notice this is 1 or less. X, the random variable x is less than or equal to 1 is what that line right there says. Random variable x just simply means what are the possibilities that are less than or equal to 1. 0 and 1 are those possibilities. So then we switch this over to an equal sign because we can do the binomial distribution with an equal. And remember, a moment ago I told you we can't do a binomial because we've removed one tomato from the stack and now we've changed the number of observations. Remember, what we're doing here is we're pulling 10 at a time. We're running all the possible ways that we can pull 10 at a time. And that takes care of the observations for us and turns this back into a binomial by setting the number of observations for us. Okay, and that's what that little 10 over 1 right here, the combinations of 1 choose 10, and right here the combinations of 10 choose 0 at a time. That's what that does. That allows us to be able to turn this back into a binomial by setting the number of observations for ourselves. Now, the observational process or the binomial process is only for equals. So the random variable x equals 1 and the random variable x equals 0. So we got to figure out both of those probabilities for those two events, right? And then we can run that through. So the way this works, and I'll leave some of this for you to pause and kind of work out some of the different pieces here, but we had p to the k power, we're choosing 1. See, there's 10 choose 1, so k is equal to 1, so 0.1 to the first power, and the probability of failure, which is 0.89, which in this case actually means that we can sell them, right, raised to the 9th power. And then on the second one, 10 choose 0.11 to the 0 power, meaning that all of them are going to be sellable. So that's that probability. Okay. Now factorials, the way factorials work is that it's that number times everything below it. Okay. So just looking at this first coefficient, we have 10 factorial over 1 factorial, 9 factorial. 1 factorial is 1, 9 factorial is 9 times 8 times 7 all the way down to 1. 10 is 10 times 9 times 8 times all the way down to 1. So you can see that there's an overlap with 10 and 9 factorial, just making that whole value right there. That first coefficient right here, okay, that entire first coefficient is 10. Now the next one, here, 0 factorial is kind of, for right now, let's just assume its a definition is equal to 1. So 0 factorial equals 1. So that takes care of that numerator piece. And then you have 10 factorial over 10 factorial, which is 1. So then that gives you those two pieces. Multiply all that stuff out, add together, and you get 0.6972. We will not deal with fractions in this. Okay, we're always going to switch these over to decimals. So the probability that we would pick 0 or 1 tomatoes out of the 10 and come up with none of them or one of them being bruised in such a way that we can't sell them would be 0.6972. Okay, that's the probability, which means that roughly 69% of the time we're going to have none or one of the tomatoes unmarketable. Okay, one or none of the time is going to work out to be 69.72. Spend a little bit of time, pause, rehash that, rewind this if you need to, and play through that a couple times. Sometimes it takes a while to really make that gel properly. Make sure you kind of have a hold of that, because on the next problem we're going to work here, on the next aspect of this, we're going to change this up a little bit. So the next piece of this, what happens if we want to know, what about if there's more than one or more of the tomatoes is damaged and unmarketable? Because this is when we start getting into the other side of this issue. All right, so the thing we do here is we do x equal to 1, x equal to 2, all the way up to x equal to 10. So there are, 9 calculations that we'd have to do there, or 10 calculations. So it's actually easier to think of this in the reverse term. Okay, so that's why I did the 1 minus p x equal to 0. So there's the possibilities for us in this particular set here is that p equals 1, p equals 2, all the way up to p equal to 10, but it's also possible that we have p equal to 0, which is the only other outcome possible. So if we do x equal to 0, the probability of picking out none, and then we do 1 minus that value, that tells us the probability of picking out 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. And we've already done the calculations for 0. That was this first value, actually, pardon me, that's the second value right here. Okay, picking 0 of them. And that works out to some value of 0.3118. So we do 1 minus 0.3118, and we get 6.882 as that probability. So that's kind of interesting. And this happens sometimes, right? The probability of picking one or more tomatoes that are damaged beyond sellability, they're unmarketable tomatoes, is 0.6882. The probability that we'd pick 0 or 1 tomatoes that are unmarketable is 0.6972. So it's kind of interesting that we actually are more likely to pick 0 or 1 is more likely that we're going to have a lot of good tomatoes rather than the likelihood that we're going to have a lot of bad tomatoes. That's what the second one says, is the x is greater than 1, meaning we have 2 or 3 or 4 or 5 or 6 or 7, or all 10 of the tomatoes we pick are not sellable. So that probability is actually smaller than the probability that we would end up with something that we can sell the entire shipment, which is good from a farming perspective, that those individuals will make out well in that. So moving this along a little bit, binomial mean and standard deviation. We can definitely find this information. To find the mean, we simply take the number of observations times the probability of success. Okay, and the standard deviation, we take that mean and we multiply it by the probability of failure. That's what 1 minus p is. Another way to write that would be q, right? That's the way I normally write, is p and q. So that'd be this, and then I multiply those three values. I multiply the number of observations, the probability of success times the probability of failure, and I take the square root of that quantity, and that gives me my standard deviation. Now, That's important because if I have that value, I can then, like going back to my previous set that I was talking about here, I have 10 that I pull out. The probability of success is 0.11, which means that the average is 0.11, meaning on average, I'm going to have one tomato that's no good. All right. Standard deviation is 0.9894, which means they can go up or down by that much. So down to 0 or up to 2. So I would think that 68%, roughly 68% of the time, that I would end up with 0, 1, or 2 tomatoes that are no good, which is pretty awesome when you think about that in terms of manufacturing and making money off of the product, right? So that's why that would be useful to us. So what else can we do with that? And think about the implications of that as well. Is now, and also notice what I said. I threw out something, didn't I? I talked about the idea that if I know the standard deviations, I know that 68% of the data would be in that realm, which that sounds kind of like a normal distribution, which is exactly what I'm talking about. We can make the binomial distribution a normal approximate distribution, which is really, really useful to us in a lot of different ways. And we can also take this a step further and turn it into a standard normal, because when we do that, then we have a z-table that we can actually use to go figure values up. Now, what I'm going to show you, the example I'm going to run through with you, you can actually use Minitab, and you can use some other softwares out there, RStudio, and if you know if you know how to do coding in R, you can have R and you can pick up libraries and all that stuff and do all this stuff in R as well. But for us, we're going to assume this to be normal, and we can run through, pardon that, I don't know why it says mean right there. Ignore that first word. It's just the normal distribution where the mean is NP and the standard deviation is, just like we mentioned it before, the square root of the product of the number of observations times the probability of success times the probability of failure. Now, let's look at a problem real quick. So the first time since 1880, this is a trend that started about 5 years ago, 10 years ago. For the first time, young adults ages 18 through 34 are more likely to live with their parents rather than living independently or with their other romantic partners. And it said it that way because, necessarily, especially during the 80s, 90s, it became more commonplace for people to live with people who they weren't married to but were romantically involved with. So although we can go through, when we want to know what is the probability that 400 or more people live with a parent given a random sample of 1,200 young adults. And then we have our successes, right, or our values there. So although approximately 32 of the young now live with a parent, this varies by gender from 35% of men and 28% of females. So 35 and 28 would be our p-values. We could look at these independently, or we could look at the group as a whole at 32. In this instance, it might be more useful to look individually at males and females rather than the other way. So right here, what we're going to look at is just going to look at the overall group, though. Okay. So the average, the mean, would be 1,200, because that's the number of observations times this probability of success, meaning they live with a parent, is 0.32. That gives us the average number of 384. The standard deviation, do that whole process, and you get 16.159, which means that's our standard deviation. That means that 68%, if we're talking about this being the standard normal, or even just standard in general, but if we talk about this being the standard normal, it means that 68% of the population is plus or minus, or is 384 plus or minus 16.1 or 0.2. All right, and we can just take it to 16 because we're talking about people, right? So it'd be plus or minus the 16. So that is quite useful information already to us. What else can we do with this? Well, what's the probability that there are more than 400 or more people living with a parent? Well, now that we know the mean and we know the standard deviation, we can subtract the mean and divide by the standard deviation, which by definition is standard normal. You do the random variable time or minus the mean divided by the standard deviation. That piece right there, that is the definition of standard normal, or our z-score or our z-value. So in this case, we do our actual value of 400 minus our mean of 384 divided by our standard deviation. And what we end up with, that's where we get this next line of z is greater than or equal to 0.99, right? Now we go to our z-table. Okay, you go to your Z table and you look on and this is, you can find these posted all over the place. Normally what you do is you go down your right-hand column and you go to where you find 0.9. Not right-hand, I'm sorry, your left-hand column until you find 0.9. And then you follow that out until you across your row until you get to where it's 0.09. And of course that means you have 0.99. It ends up being the very last column in that row for 0.9, right? And that value you come up with in that spot is 0.8389. Now some of you are thinking, well, why isn't that the probability? Why do I do 1 minus that? Because those tables are set up to find everything below it. So what you actually found, I know we're saying Z is greater than 0.99, right? But the way that table is set up is that Z is less than or equal to 0.99. That's the way that table is set up. So we got to do 1 minus that to find the other direction. You can even see that. You can see this very visually when you look at the top of the table. It'll actually have the stuff to the left of 0.99 or whatever that value for X is shaded in, meaning that is adding up cumulatively from left to right. So 0.8389 is the probability that 400 people or less live with their parents in that age group, right? But we want to know what's the probability of 400 or more people live with their parents. So we need to do the opposite of that value, which means you need to do 1 minus that, which is 0.16, or roughly 16% of the population would live with their parents in that age group. Now, this is for this sample that we're dealing with, the sample of 1,200 people, right? That's what we would expect to find. Is the 0.16. So if we were to randomly pick one member of that 12,000 people, the probability that that individual lives with their parents is roughly 0.1611. Okay, 0.1611. All right. So I hope this was useful. I'll try to run through these examples and make these fairly exhaustive in nature. If you need more examples, you need more explanation, please reach out, leave a comment, shoot me an email. Find more videos even. Rewatch this one and hit pause a lot and rewind. But keep working on it. Statistics matter and they do count too, all right? Anyway, take care. Have a good day.